Welcome back. Yesterday we took look at the remainder theorem, and today we're going to take a look at another theorem called the factor theorem. I'll just go back to yesterday's lesson really quickly. Again, I think that was one of those lessons where you may have felt like things were pretty abstract and weird throughout, but in the end, what did we exactly do? We realized that if you plug a number into a polynomial and it gets a result of whatever, you get 7 out, then it means that when you divide by x minus whatever you plugged in, you have a remainder of 7. That was pretty much it. And I think you're going to see something similar today where it may seem a little abstract as we go, but by the end of it, we can summarize it pretty easily. I'm also going to mention that, mention and make a confession at the same time. I forget all these theorems names and which one is which and what does what, and it doesn't matter. Frankly, we just kind of use the math and we don't think about what it's called. I mean, think about it this way. If we didn't know what a square was called, but we knew what the exponent of 2 did, we would still know how to do math. We just forget the name for it. And the theorems that we're going to learn this year are kind of the same. They all work very similar, and they all kind of have the same kind of direct effect on the polynomials that we're looking at. So we're not going to worry too much about naming them, except that because I'm teaching you a lesson, I try to actually point out what the names are. Anyway, let's jump into the factor theorem. It's me again. Wait a second. Okay, there we go. We only need one screen with me on it. The factor theorem. Basically, let's jump in by taking a look at an example, which is pretty much a review of yesterday, what was covered, and go from there. So for question 1, we want to find the remainder of the polynomial x cubed minus 2x squared minus 5x plus 6 when it's divided by each of those three binomials, x minus 3, x minus 1, and x plus 2. Now notice it didn't say I have to actually divide them, it just said I have to find the remainder. Finding the remainder is actually pretty straightforward. To find the remainder when I divide the polynomial by x minus 3, I just find out what its value is at, I should put remainder. Remainder equals, I just plug in x equals 3 and see what I get. 3 cubed minus 2 times 3 squared minus 5 times 3 plus 6. 27 minus 18 minus 15 plus 6. That's 9. Yep, that's 0. Okay, so remainder of 0. Cool. How about this one? I won't bother writing remainder because I don't really have the room, but we want to do or plug in x equals 1, and that's just going to be 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. Negative 1, negative 6 plus 6. Hey, that's 0. And the last one, we'll plug in x equals negative 2. Just barely fit it on the page, but that's okay. Making sure we don't make any sign errors. That's negative 8. Negative 2 times 4 is negative 8. That's plus 10 plus 6. So negative 18, or negative 16 plus 16 is 0 again. Okay, so now if we're thinking about it, if something is divisible by a binomial and has no remainder, that means it is divisible by the polynomial. So we just found 3 factors of that particular polynomial. So I know that x cubed minus 2x squared minus 5x plus 6 must have factors of x minus 3, x minus 1, and x plus 2. Now there may be another factor, but I think you'll notice that since this has x, 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 and this has an x cubed, there can't be any other factors in there. So for instance, there could be a number in front of this factored form, maybe a 3 or a 5 or something, but that would give a 3 or a 5 in front of the x cubed polynomial on the other side. What that basically means is that by finding those 3 zeros, finding those 3 things that had a remainder of 0, we found the factored form of the equation. Okay, so big deal. What difference does that make? I want you to stop and think about this for just a moment. We spent grade 9, 10, 11, or at least 10 and 11, focusing on how to factor trinomials, things where the biggest degree was x squared. We just factored a quatrinomial, something with degree 3 in it, for the first time ever, and it wasn't actually that hard. It was kind of a coincidence that we had these nice values up here that worked out, but we still did it. We still factored a quatrinomial, and it wasn't too bad. Incidentally, there is a quatrinomial formula, one that solves x cubed things like this. It's a little bit like the quadratic formula, except that the quadratic formula, which looks a little confusing, it's like, it's not huge, it's reasonable sized. The quatrinomial formula is actually like a booklet. The formula is a booklet, not the solution, just the formula is a booklet, a rather large booklet. So we don't want to have to use it. We want to use a method similar to this. Let's see if this always works. First thing we're going to do is just expand that out and make sure that it actually does work. So I'm going to do x minus 3, x minus 1, x plus 2. And because I get to choose which order I'm going to expand this in, I'm actually going to leave the first term the way it is and expand the last two. And I'm going to do a little bit of this in my head because we should be getting good at this by now. We're going to have an x squared, a minus x, and a plus 2x is just going to be plus x, and a minus 2 at the end. And now when I expand that out, I should get temporarily 6 terms. That'll be an x cubed plus x squared minus 2x minus 3x squared minus 3x plus 6. It's x cubed minus 2x squared minus 5x plus 6. And sure enough, that is what we started with. So it looks like we factored that correctly. Pretty cool. And that brings us to the factor theorem for today. X minus b, whatever b is. In this case, our b's were 3, 1, and negative 2. But x minus b is a factor of the polynomial p at x if, with two f's, the polynomial evaluated at b is equal to 0. And for those of you who haven't seen it before, and some of you may have, if with two f's means if and only if, which means it's two-way condition or two-way true. If the polynomial evaluated at b is 0, then x minus b is a factor, and if x minus b is a factor, then the polynomial will be 0 when evaluated at b. Not all theorems are two-way conditional. I won't get into the mathematics ones, but for instance, if I said I had a dog, that doesn't necessarily mean I have a chihuahua. But if I tell you I have a chihuahua, I do have a dog. That's one-way conditional. Another theorem that you may be familiar with that we could have introduced this in is the Pythagorean theorem. A squared plus b squared equals c squared if you have a right-angled triangle, and if you have a right-angled triangle, then a squared equals b plus b squared equals c squared. It's two-way conditionally true. So anyway, basically this is just a modification or a slight difference to yesterday's thing, which says if we plug in a value and get a 0 out, then we know one of the factors. And if we know one of the factors, we know it'll have a remainder of 0.
Oops. Let's fix the little typo there. Right here, that says the wrong thing. It says the polynomial evaluated at a over b. That should be the polynomial evaluated at b over a equals 0. So just make that little note in your whatever you're writing right now. I'll change it on the handout, but please be aware that that should be a b over a, not an a over b. And if you're wondering why that's true, if ax minus b is a factor, then I can factor out a from both of those and get that. And then this part here is essentially the same rule as that right there. Anyway, I will fix that. My apologies.
Okay. So let's use the factor theorem along with any other factoring methods we know to factor that polynomial. Now that polynomial is rather huge. It's a degree 5 polynomial, keeping in mind that until about 4 minutes ago, we had never factored anything really bigger than an x squared polynomial. Now we did an x to the power of 3, and now we're going to just jump straight into an x to the power of 5. Okay, so here's what we need to do. We don't have any factoring methods that are going to let us do a lot here. As far as, I can't do difference of squares, common factor, there's nothing there. I could common factor this if it's possible to common factor a 5th degree polynomial, but there isn't one. I can't use factoring a trinomial, simple or complex. I'm kind of stuck. But I can use the factor theorem. If I can find some value of x that makes that 0 when I plug it in, then I know one of the factors. So here's what I'm going to do. I'm going to try just a couple of things. Let's try maybe x equals 1. So if I plug in x equals 1, then what I can do is say, okay, 1 to the 5th minus 9 times 1 to the... You know what? This is going to be very time consuming. So what we're going to do is just do this mentally, because plugging in 1 is really, really easy. That's 1. I don't want crayon. I'm not a child. I just want red. Okay. 1 minus 9 is negative 8. Plus 22 is positive 16. No, 14. Negative 8. Yeah, 14. 14 minus 6 is 8. 8 minus 23 is negative 15. Hey, it works. That's 0. So the polynomial at 1 is equal to 0. So x minus 1 is a factor. Okay, big deal. We found 1. Clearly there's some more. But here's what we can do. We should be able to now divide... Oh, by the way, the fact that that worked out in the first shot is either an incredible coincidence or I made it that way. If it hadn't worked, we would have tried other easy to plug in values like negative 1 or 2 or negative 2 or 3 or negative 3. They could be fractional, but we're going to try the integer ones first and see if we find any that work. So now what I can do, and unfortunately this is the tedious part, is I have to do a long division. X to the 5th minus 9x to the 4th plus 22x cubed minus 6x squared minus 23x plus 15. And I have a feeling no matter how much room I had left for this, I would have ran out of room. But we'll see what we can do. X minus 1, we just said was one of the factors. So there should be a remainder of 0, but we need to know what the quotient is. So I'm going to say x to the 4, which is going to be x to the 5 minus x to the 4. Negative 9 minus negative 1 is negative 8. Plus 22x cubed. This will be a minus 8x cubed. And when I multiply that by negative 1, I get plus 8x cubed. 22 minus 8 is 14. Minus 6x squared plus 14x squared minus 14x squared. Negative 6 minus negative 14 is positive 8. Multiply by 8x. Oops. Should be a minus 8x. No, it should also be a 23x. Minus 8x. 1 second here. Ooh, okay, so I had a little heart attack there. Realized I have a sign error. That should be a minus in front of the 23x from when I brought it down. Okay. Negative 23 minus negative 8 is negative 15x. Bring down the plus 15, and that should just be a minus 1. Sorry, minus 15. And sure enough, the remainder is 0 as we suspected it would be. Okay, so now we have this polynomial here. Just go around it. That times x minus 1 is our original polynomial. So now I have to see, can I factor the x to the fourth polynomial? So tedious, but I think we can do it. Okay, so we have to look for something else that may possibly make that equal to 0. Just for the heck of it, I'm going to try 1 again. When I plug in 1 there, I'm going to get 1 minus 8 is negative 7, plus 14 is positive 7, 7 plus 8 is 15, and minus 15 is 0. Okay, so it looks like I have another factor of x minus 1, which of course may or may not be a coincidence. I may have set it up that way, just because I don't want to check a million values. But if I take that polynomial now and do x to the power of 4 minus 8x cubed plus 14x plus x squared plus 8x minus 15, and I do long division on that, I'm going to get a x cubed negative 8 plus 1 is negative 7 x cubed plus 14x squared. I'm going to multiply that by negative 7x squared. That'll give me a plus 7x squared there. 14 minus 7 is 7. Bring down the 8. Plus 7x. 7x squared, minus 7x. That gives me 15x minus 15 plus 15. There we go. And we get a 0 again. Okay. So now we have that polynomial and 2 factors of x minus 1, since we divided out an x minus 1 there and an x minus 1 over here. Now, could we divide that again? The answer is probably, but I'm really running out of space. So what I think I'm going to do is just really quickly insert the blank document, and then we'll continue from there. Okay, with the magic of pause and a blank document, we left off with having that polynomial, which we're still trying to figure out if we can factor it. Again, let's try some values. I'm going to try x equals 1. When I plug that in, I get 1 minus 7 plus 15. That's not 0 for a change, so that one doesn't work. So now I'm going to go on to, let's say, negative 1. If I plug in, I want x equals, I just want to plug in negative 1, just to keep track. Again, I'm going to try and do this one mentally. That's going to give me negative 1 minus 7 is negative 8. Plus 7 is, that's not 0. That's all that matters. We don't have to go any further. So let's try 2. That's going to give me 8 minus 28 is negative 20. Plus 14 is negative 6. It's not equal to 0. Okay, let's try negative 2. It's getting to the point where maybe I should actually write something down. Negative 2 cubed minus 7 times negative 2 squared plus 7 times negative 2 plus 15. Negative 8 minus 28 minus 14 plus 15. Too much negative, so it's not equal to 0. Let's try 3. Notice I'm just kind of systematically going through. If it was divisible by x, it would be obvious because it would be an x at every term. Then I tried 1, negative 1, 2, negative 2. I'm just trying the smallest numbers. You could guess 27, but You can spend a long time doing that. If we plug in 3 cubed minus 7 times 3 squared plus 7 times 3 plus 15, 27 minus 63 plus 21 plus 15. That's going to be 36, negative 36 plus 21. Hey, actually that one will equal 0. Okay, so that means we just found a factor of x minus 3. So I'm going to make a little note here. Yay. Okay. So now we have to do that polynomial divided by x minus 3. I hope you invested in paper this semester. We may use a little bit of it. By the way, this is like the most tedious question we're going to do, so once we're done this, it's out of the way. Okay, I'm going to multiply that. X squared gives me x cubed minus 3x squared. Negative 7 minus negative 3 is negative 4. Bring down the 7x. Negative 4x gives me negative 4x squared plus 12x. Gives me negative 5 plus 15. Sorry, negative 5x plus 15, and I do negative 5x plus 15 equals 0. Okay, so that's a factor. Now I could do the same thing again and use the remainder theorem, except I'm going to look at that and say, hold on, x squared minus 4x minus 5. Now we're down to a trinomial again. It's a simple trinomial. Let's see if we can factor it using just our regular method of saying we want to multiply to negative 5, add to negative 4. And can we find any two things that do that? And again, multiplying to negative 5 means one's positive, one's negative. So the bigger magnitude is negative, the smaller one is positive, and it's going to be negative 5 and plus 1. So that means that this is equal to x minus 5, x plus 1. Okay, so when all is said and done, what does that mean? It means, and this is going to be a big one. Well, not a big one, but a big one to write. Our original polynomial, x to the 5th minus 9x to the 4th plus 22x cubed minus 6x squared minus 23x plus 15. Getting dizzy just writing that out. Well, the first thing we did is we found out it was divisible by, was it x equals, or x minus 1? So I just flip back to the other page here. So, yep, we had an x minus 1 and another x minus 1. So now I can say we have factors of x minus 1, x minus 1, and then we found an x minus 3, and then our final two were x minus 5, x plus 1. Okay, and that is perfectly acceptable. Now, I did put equals here. It should actually, again, have a possible coefficient in front of it, but because there's no, or a coefficient of 1 in front of the x to the 5th, I know that that coefficient is going to be a 1 anyway. I can try to write this just a little bit nicer by putting them in kind of order from smallest to largest, not that it's required. So x minus 5, x minus 3, x minus 1 appears twice, and x plus 1. Okay, so that should be my final answer to the whole thing. So coming back over to our original page, see other sheet. For more details, our final answer was x minus 5, x minus 3, x minus 1 squared, x plus 1. And it says to verify our answer using both MathWay and Desmos. So let's take a moment and see if we can do that. Okay, so popping over to MathWay, what I'm going to do is type in my original polynomial, x to the 5th minus 9x to the 4th plus 22x cubed minus 6x squared minus 23x plus 15. Click that over here, and I'm going to ask it to factor it for me. And when it does that, it is unable to solve the problem. Did I type that in incorrectly? Or have I actually broke MathWay? X to the 5th minus 9x to the 4th plus 22x cubed minus 6x squared minus 23x plus 15. Wow. That may have broken MathWay. So, if I can't verify it that way, what I could do is plug in the opposite, because factoring is very difficult to do for large degree polynomials, but expanding is pretty easy. So let's try x minus 5, x minus 3, x minus 1 squared, x plus 1, and see if it'll expand it for us. Simplify, yeah, that's what we want. And we get x to the 5th minus 9x to the 4th. Did I type it in right? I think so. Minus 6x squared minus 23x plus 15. So, yeah, it looks like we've just been able to verify it using MathWay. Now, can we verify it using Desmos? Okay, so how do we go about this using Desmos? Well, let's type in our original polynomial. I'm going to type in y equals because I want a function as opposed to just a polynomial. But y equals x to the 5th minus 9x to the 4th plus 22x cubed minus 6x squared minus 23x plus 15. And that gives us, to say the least, an interesting polynomial. I'm actually going to expand that out just a little bit, or make it a little bit easier to see. I wanted to go from about -2 to 6. Oops. Yeah, that's fine. We'll do that. -2 to 6 for the y. No, I did want this one. I do want the x values. -2 to 6. Is the y looking okay? Let's get the y out entirely and then I'll switch it again. -2 to 6. Okay, at least I can see the whole thing at once. So that's what that polynomial looks like. It is a degree 5. I'm going to just zoom out and you'll see that at a distance it looks kind of like the y equals x cubed or y equals x to the 5th functions. Any odd-powered function. Okay, and now I'll verify it by typing in my factored form, which is y equals x minus 5, x minus 3, x minus 1 squared, and x plus 1. And sure enough, those two look pretty much identical to me. So that's how I would verify it using Desmos. I personally like using Desmos to do graphical proofs like this, or graphical verifications that my answers are right. But if you'd rather use MathWay, you're more than welcome to. Oops. There it is. Okay, so coming back to our lesson, which is going on way too long. We got our answers pretty quickly. I do want you to notice, or sorry, pretty quickly, relatively speaking. It was kind of tedious. But I want you to notice that our zeros, let's just go back up here for a second. The zeros that we got, -5, -3, -1, +1, it is not a coincidence that those are all factors of the constant term 15. They all are factors of 15. And what I'm going to suggest and show you the theorem for in just a moment is that you don't have to check every possible number. Like I said, check plus and minus 1, plus and minus 2, plus and minus 3. You only have to check multiples of 15. Or factors of 15, I should say. So plus and minus 1, plus and minus 3, plus and minus 5, and plus and minus 15. That's it. That's all of them. And that's going to make our life easy if we can actually narrow it down quite a bit to realize that those are the only ones we need to check. The only little trick there is that just checking that plugging in the number makes the polynomial 0 doesn't tell you what order it is, which is why we got 2x minus 1s. We had to do the same thing, divide and do it again. Okay, so the integral 0 theorem, another theorem, too many names. Basically, looking back here, it says exactly what I just said. We only have to check plus and minus 1, plus and minus 3, plus and minus 5, and plus and minus 15. All the factors possible for the constant term 15. That's why it's called the integral 0 theorem. We're looking for integers that give us 0. That makes sense, hopefully. What about if the factors are not integers? They're fractions. And if they're fractions, then we use the rational 0 theorem. Now this is a little bit similar to the way we did factoring complex trinomials. Instead of looking for the end number, we're looking for the end number times the first number, or in this case, n number divided by first number. So here's what I'm going to do. I'm going to look at the last number, the minus 4, and I'm going to look at the first number, positive 2. By the way, the sign won't matter since we're doing plus and minus checks anyway. And I'm going to say any factor that we have should be a factor of 4, or minus 4, over a factor of 2. So that could be, just draw an arrow, because this isn't really equal to anything. It's just possible numbers to look at. I can try on the top 1, and I will just remember in my head that it's plus or minus. 1, 2, or 4, and on the bottom 1 or 2. So all the possible fractions that gives me would be 1 over 1, 1 over 2, 2 over 1, 2 over 2, which is already there, it's 1, 4 over 1, or 4 over 2, which again, 4 over 2 is 2, it's already on our list. And these are all plus minus, plus minus, plus minus, plus minus. So we only actually have to look at 8 different factors in order to get this. Well, again, we get to choose which one we want to do first of our 8. I would suggest that plus 1 is always going to be the easiest one to look for. So let's try, let's try plugging in plus 1. The polynomial at 1 will equal 2 minus 9 plus 2 plus 9 minus 4. Yep, that's 0. That one works. So we found one of our factors. We could try doing more now, or we can do long division, find out our third degree polynomial and work from there. It's up to you. I might say trying -1, 2, and -2 are easy, so let's just see what happens. -1. Okay, so we try -1, we get out 2 plus 9 plus 2 minus 9 minus 4. And that one works. So we found 2 of our factors. Let's try the 2's. 2 times 2 to the 4. 2 to the 4 is 16, so it's going to be 32. 9 times 8 is 72, plus 9 times 2 is 18, minus 4. I don't know what that is, but it is not 0. At negative 2, we're going to get 32 plus 72 minus 18 minus 4. That is not 0. Okay, and at this point, I'm going to say we've tried a few of them. We could try the half, we could try the 4, but I'd say we just start getting into long division. It's not going to be that bad for this one. So let's do the long division for the x minus 1. Actually, you know what? No, let's not do that. Let's actually try all the factors. Because if we can find 4 different factors, then we're done factoring. We don't even have to do anything else. So this may be a little tedious, but I think it's less tedious than long division. So let's try it at 4. And that gives us 2 times 4 to the power of 4. Ooh, this big number. Is that 256? Minus 4 to the power of 3 times 9 minus 576 plus 9 times 4 why am I doing the math on this? Plus 32. Oh, sorry, I'm missing. Oh, did I miss a term in the last ones? Okay, I'm going to cheat for a second because I feel like cheating at the moment. And I'm going to go over and actually try to see if I can find any of the zeros of this. So just to save myself some time, I'm going to go to MathWay. Okay, and I'll show you kind of a cool way to do this. I'm going to say that a function is equal to, and the one that we want is 2x to the power of 4 minus 9x cubed plus 2x squared plus 9x minus 4. Okay, so now what I'm going to actually do is just plug in for the x right there, the first x, the f at x, what I want it to evaluate at. So I said I wanted to evaluate it at 1, and yep, the answer is 0. So that one worked. Stop trying to get me to pay. I'm going to do it at negative 1. And it evaluates it. The answer is 0. I'm going to evaluate it at 2. The answer is negative 18, so that doesn't work. I'm going to evaluate it at negative 2. The answer is 90. It doesn't work. So I think I screwed up the math when I was doing it manually. I just missed a term, but I also don't think it matters. All that matters is that they're not equal to 0. Then I wanted to do it at 4, which started to get a little tedious. That's equal to 0. Okay, that's good. And minus 4, not 0. And then we have to check those two fractions. A half, and that's a 0. And I think this is, like, it's not going to work, but we'll try it at minus a half. And it's equal to a bunch of weird stuff. Okay, so going back there, here's what we found. F at 1 is equal to 0. F at negative 1 equals 0. F at 4 was equal to 0. And F at a half was equal to 0. And because this is a 4th degree polynomial, I know that it's going to equal something. Let's just try this. We know that the factors are going to be x minus 1, x plus 1, x minus 4, x minus a half. Now here's the thing, if I multiply all four of those brackets together, I'm going to get out a 1x to the fourth term, but I know from up here that I want it to be 2x to the fourth, so I can put a 2 in front of this. And I'm going to just make my life a little nicer and actually put it into that bracket. And that will get rid of the fraction. And that's where the rational zero theorem comes in. I get a rational fraction, which just basically means that my polynomial, or sorry, my binomial has an a or a non-zero initial term. Okay. Thankfully, that means we're done. That was a little bit tedious and brutal, but I think you get the point. We can use this method, and you know what? I'm not even going to really distinguish between the rational zero theorem and the integral zero theorem. They're just together the zero theorems. And basically the idea behind them is simple. If you can find a number to plug in that gives you 0 out, it's a factor. And if you want to see which numbers you should try plugging in, if the first coefficient is 1, then just try factors of the last value. If it's equal to a number other than 1, try, like we did up here, all of the factors of the last number divided by all the factors of the first number. So basically all we saw today was if you can find something that gives 0 when you plug it in, it's a factor. And the ones that you should try are the ones using the integral zero method and the rational zero method. You're not going to get any better at these unless you just try some. So that's what I would like you to do now. And I did mention one hint, and that's that for 17b, one of the integer roots is order 2, which means that if you try to find all of the, you're going to have to do long division at some point because you don't know which one it is until you've divided it out and see if it's still there again. Anyway, give those a shot. Let me know if you've got trouble. Otherwise, I will see you in the next lesson, which will, I pray, be much shorter. Bye. Have a good day.